If you look at page 4 of your worksheet, distinguish between free oscillations and forced oscillations. So just now we actually went through the characteristics of both. Now for free oscillations, you can just say that the body oscillates with no external forces applied, which is related to what I just mentioned to you just now. After you give your body an initial disturbance, there is no longer any forces acting on it. So maybe I make a note here. After the body is given an initial disturbance, there is no longer any force acting on the system. Okay, so that's why we can say body oscillates with no external forces applied. When you apply your initial disturbance, there is force, but once you release it, there's no more force. And it's at that point your object starts to oscillate. Then after that, the last one, what is forced oscillations? Forced oscillation, your body can only oscillate when an external force is applied. If you say when an external force is applied, you can also kind of replace this with body can only oscillate as long as an external periodic force is applied. So just use either one. Now for part B, they mentioned to you that a trolley is held on a horizontal surface by means of two stretch springs as shown in the figure. One spring is attached to a fixed point, the other spring is attached to an oscillator which causes horizontal oscillations of the trolley. So the oscillator vibrates with a constant amplitude of vibration. The frequency of vibration of the oscillator is gradually increased from a very low value. And subsequently, the variation with frequency f or the amplitude x0 of vibration of the trolley is as shown below. So right now, what you have is this trolley right over here. It's connected to two springs on either side. One particular spring is connected directly to an oscillator. So this oscillator will actually cause some sort of vibration. It will actually move left and right in this manner. When it moves left and right, it will in turn cause the spring to move, and then after that, the trolley will also move along with it. So here, if your oscillator was oscillating at a certain frequency called your driving frequency, your trolley would also oscillate with that same frequency. Okay, because this one here is your forced oscillation system. All right, it is being forced to vibrate by the oscillator. So whatever frequency of vibration that your trolley is oscillating at, it is the same as that of the oscillator itself. So in your question, they mentioned that the frequency of vibration of the oscillator is gradually increased from a very low value. This also means that the frequency of vibration of the trolley is also increasing also from a very low value. So when the trolley was then oscillating, what they did was that they measure the amplitude of oscillation. If say this one here was your equilibrium position, for example, your trolley will vibrate left and right in this manner here. So what you want to do is you want to measure the amplitude. Now the thing is that if you're using different frequency for oscillator, your trolley will oscillate with a different frequency also, and their respective amplitude will also be different. So right now you are interested in finding out how does the amplitude vary with the frequency of vibration of your trolley. So that is shown by your graph below here. This is showing you the variation of the amplitude of oscillation of the trolley with the frequency of vibration. It is this little curve here. So from the notes last week, I already mentioned to you that this one is actually your resonance curve. So from here, there's one particular point that is always of interest to you. You always want to look at where is the point where you have maximum amplitude. This point here is where you have maximum amplitude, isn't it? This point here is where resonance occurs. So at this particular frequency here, where you have maximum amplitude, where resonance is occurring, this particular frequency here is where your driving frequency equals to your natural frequency of vibration. So last week I did mention to you that all systems, all oscillating systems have their own natural frequency of vibration. It's just that when you're talking about free oscillation system, it is actually readily shown. But if it's a forced oscillation, it's not readily shown. All right. So your trolley here actually has its own natural frequency of vibration. It just so happens that when your driving frequency equals to the natural frequency of vibration, your trolley now oscillates with the maximum possible amplitude. This is what we meant by resonance then. So why am I explaining all this? Is because the next part of the question asks you to deduce something out. They ask you to use the figure that you had from before to determine the value of natural frequency of vibration of the trolley. So from that figure that you have right over here, find out what is the natural frequency of vibration of the trolley. We want to determine this natural frequency. So you need to single out where is the part where you have resonance in the first place. Because at resonance, the driving frequency that you had is equals to your natural frequency then. So if you read your graph carefully, it will be some value. On my case here, I can't really read it properly because my lines are actually a bit thick. So I'll just refer to the answer straight, okay? You can actually read it from your own graph, all right? So if you wanted to word your answers, you will actually say something like this. At resonance, the trolley is vibrating at maximum amplitude when the driving frequency equals the natural frequency of the trolley. So from the graph itself, you can actually see that the natural frequency is 2.1 Hertz. The marking scheme allows you to have a range to your answer. I mean, they give you a range. As long as your answer falls within the range, you should be fine. Anything between 2.08 to 2.12 Hertz would be acceptable. So here you need to make use of concept of resonance. Find out where is vibrating at maximum amplitude. When you find out where it's vibrating at maximum amplitude, you already know that's the point where driving frequency equals natural frequency. So if you read the value from there, you will get 2.1 Hertz, which is roughly here. This is where you get 2.1 Hertz. Then I'll move on to the next part. Now, in part 2, state whether are there any frictional forces acting on the trolley. So recall that last week I mentioned to you, if you're looking at the resonance curve on page 3, if you do not have damping, you do not have resistive forces or anything, your resonance curve will be something like this. Your case here is no damping. You have infinite amplitude. This was what I mentioned to you last week. So you don't see a peak to your resonance curve. That means there's no damping forces. There is no frictional forces. So looking at your graph here, it is not infinite amplitude. There is a limit, there's a peak to it. So here you would word your answer as something like this. The amplitude is not infinite, so frictional forces are present here. Damping forces are present here. So that's for this particular question here. Then I move on with C. Now in part C, they mentioned this. The oscillator in B is now stopped. The trolley is given an initial horizontal displacement of 4.7 centimeter along the line of the springs before it is released. From here, find out the maximum speed of the trolley. Okay, so this is a new situation that's being described here. Now, when they tell you that the oscillator is now stopped, and then after that, they subsequently give you a horizontal displacement to the trolley before releasing it, your system now becomes a free oscillation system. Because here you're giving an initial displacement and then releasing your trolley. So looking at how the diagram looks like for your current question, you can see that even if your oscillator is switched off here, And then you're only left with these two springs and your trolley in the middle. If you were to displace your trolley towards the side by say 4.7 centimeter to this position, and then you release it, your trolley will just oscillate back and forth in this manner. So in your current case now, without the oscillator being switched on, you give it initial displacement, you release it, it starts oscillating. This is now free oscillation. Okay, it's now oscillating freely. So that's the significance of the first two statements there. Your system now becomes a free oscillation system. And then after that, there's also another thing that you should be able to deduce from here. When they told you that the initial displacement given to the trolley was 4.7 centimeter, this would actually be your maximum possible amplitude. It will be 4.7 centimeter. So last week I mentioned to you, whatever displacement you gave to your system, and then your system starts to oscillate, the amplitude will never be greater than what you gave it. If you gave it an initial displacement of 4.7 centimeter, the highest your amplitude will ever go is going to be 4.7. It will never be higher than this because of energy conservation. It can only go less because of energy losses, but it can never go more than that. All right. So knowing those two facts here, how do you find your maximum speed? Your maximum speed, you already know Vmax is equals to omega x naught. All right. So your omega is 2 pi f. Your x naught remains the same. Now, what's the value of frequency that you want to use? Okay. So right now, I already told you that your system is oscillating freely. It's a free oscillation system. I also mentioned last week that when you were having a free oscillation system, when it oscillates with natural frequency. So for this part here now, when your trolley is oscillating, it is actually oscillating at natural frequency. Its frequency of oscillation is the natural frequency itself, which you already found at the top here, 2.1 hertz. So if you use 2 pi f, it will be 2 pi times 2.1. And then your amplitude, you use the maximum possible amplitude value, it will just be 4.7 centimeter. Remember to change it to meter, you're going to get 0.620 meter per second. Next one, have a look at page 13. So you have a metal block that hangs vertically from one end of the spring. The other end of the spring is tied to a thread that passes over a pulley and is attached to a vibrator. All right. So here you have metal block attached to a spring. One end of your spring is tied to a thread passing over a pulley that is attached to a vibrator. So here they mention this, your vibrator is switched off. The metal block of 120 gram is displaced vertically and then released. The variation with time t of the displacement y of the block from equilibrium position is as shown here. So there's something here that you should be able to deduce again based on what they mentioned, being that the vibrator is switched off. So when your vibrator is switched off and they give it an initial displacement before releasing it, this is again a case where your system is a free oscillation system. The system is oscillating after being given an initial disturbance. There's no other periodic force being applied here. All right. So it's a free oscillation system. And your graph here is showing the variation of displacement with time. So one thing that you should be able to note here now is that this frequency f here that your mass is oscillating is actually your natural frequency already, since it is free oscillation right now. Whatever frequency you have here is already the natural frequency itself. So this one will come into play later. Here, the question just asks you to find out angular frequency first for the first part. For the vibrations of the block, calculate the angular frequency omega. So you find out what is your period. Because omega is 2 pi over t, so you need to find out your period first. Your period is this one. So this one is actually going to be 0.6 seconds. Okay, so this is your period. So sub your values in 2 pi over 0.6, you will get 10.5 radians per second. Very easy question for 2 marks. So if this is okay, then you move on to the next one. Now, the next one is asking you about the energy of vibrations. Find out the energy of vibrations for that system here. So before we go to that, notice that in your current case, when the system is oscillating, the amplitude actually did not decrease at all. You see right over here, the amplitude did not decrease at all. Here you see amplitude remains constant. That means energy is constant throughout. So you don't really need to be particular about which point you pick. Any point you pick on the wave, total energy will be the same. Okay, let me just write the term clearer here. Amplitude remains constant, total energy is constant throughout. Okay, the KE and PE can change, no doubt, but the total energy will be the same throughout. So in your case here, if you want to find total energy, that time I mentioned to you, total energy is actually just your KE max, which is half m omega square amplitude square, right? So here, it doesn't matter which point you pick for your amplitude to find the total energy, it will be the same throughout because total energy is the same here. All right, so it doesn't matter which point you pick. You can pick this, you can pick this, you can pick this, you can pick this, no matter. All right. So here you want to find the total energy. As I mentioned, it's just going to be KE max, half m omega square x naught square. Sum in the value of your mass, which was 120 grams, is already stated here, 120 grams. Sum in the value of your omega, which is found in part 1 here. Don't forget to square your answer. And then sum in the value of your amplitude. Your amplitude, if you look from the graph, is actually 2 centimeter. All right. So remember to change it to meter. And don't forget to square it also. Eventually, your answer will become 2.65 times 10 power minus 3 joules. So it's pretty straightforward. Now, if you look at part B, for part B, your vibrator is now switched on. And then the frequency of vibration is varied from 0.7 F to 1.3 F, where F is the frequency of vibration of the block in A. So the significance of having your vibrator being switched on now, which subsequently cause your mass to oscillate, is that this is now a forced oscillation system. Okay, that's what we need to identify from here. It is now a forced oscillation system. They mentioned that the frequency is varied from 0.7 F to 1.3 F, where F is the frequency of vibration of the block in A. So the block in A is this one here. And they say that the frequency, the F is the frequency of vibration of the block. But in A just now, I mentioned specifically that this part is where your vibrator was switched off. You gave it initial displacement and then you let it oscillate. This is free oscillation. So whatever oscillation you're getting right over here, the frequency would have been the natural frequency itself because it was oscillating freely. So you can think of F here being the natural frequency. So that's what you can identify here. So you vary your driving frequency from 0.7 F to 1.3 F. Then here they ask you to complete the figure below to show the variation with frequency of the amplitude or vibration of the mass, and then label this line A. So this particular part here, F, is actually your natural frequency. So if you're talking about this part being your natural frequency, this F here being your natural frequency, when you want to draw your curve, resonance curve for amplitude versus frequency, it will just be something that looks like this. But please make sure that the point where you have A max, maximum amplitude, coincides with your F. Okay, because it's only when your driving frequency equals natural frequency that you get maximum amplitude. So just draw the green line. Okay, it can be any line. You can draw it slightly upwards like this or downwards like this. It doesn't matter as long as you have that general shape there and the peak is at natural frequency. Then if you look at part C, now part C is saying that some light feathers are not attached to the block in B to increase air resistance. The block now has some feathers attached to it to increase air resistance. Now when you attach feathers to increase air resistance, this is actually saying that damping is increased. It's not damping is introduced. Damping is increased in the system. So here they mentioned that the frequency of vibration is once again varied from 0.7 F to 1.3 F, where the new amplitude of vibration is measured for each frequency. On the same figure, draw a line to show the variation with frequency of the amplitude of vibration. So this one, since you have increased damping here, damping is increased, your new line ought to follow three things. This one was mentioned in the notes before. This is on page 3. With increased damping, your whole graph line must be lower, your graph must be flatter, and then after that, the frequency at which you get maximum amplitude ought to be shifted a little to the left, or you can maintain it as it is now. All right. So here, your new graph ought to be like this line here. So you look at what the marking scheme said, the peak line is always below the peak line A. This is talking about graph line always lower than the one before. And then after that, the second point was the peak is not as sharp. This is talking about the peak must be flatter. And then after that, the third thing here was that and at frequency or peak in line A. This one, you look at the statement that I highlighted in pink. This one accepts your peak frequency being at the natural frequency itself. And at frequency or peak in line A, the marking scheme accepts it as your peak being at the natural frequency itself. There were no issues. But that time I mentioned that you could also shift the frequency slightly towards the left, like what is being shown right over here, like this. You see this one here, this one was my A max, right? But the frequency at which it occurs is slightly less than the original frequency, right? This is you already shifting it slightly towards the left, or slightly less than the original frequency. So your marking scheme actually allows both. You should just focus your attention to this last statement. They say either at the frequency itself or slightly less than the frequency. Notice the word or. So they actually allow you to have either one. Okay, that's what I meant by this point here last week. You could choose to follow the third point, or you can just choose to ignore it. All right. Either you use the same frequency as before, or you shift the frequency slightly towards the left when it comes to the maximum amplitude. So it doesn't matter which one you have. But the first two is really important to follow. The graph line is always lesser than before, and it must not be as sharp. It must be flatter. So these 2 points are the ones that are most important. The third one, not really. Okay. Okay, this one is March 2018 P42. So what is meant by natural frequency of vibration is the frequency at which a body will vibrate when there's no external force acting on it. The marking scheme actually gave two different variations. They say the frequency at which the body will vibrate when there's no driving force acting on it, or the frequency at which an object will vibrate when there's no resistive force acting on it. But you can actually summarize those two terms, driving force and resistive force, as just one convenient term called external force. It is the frequency at which an object vibrates when there is no external force acting on it. External force here already means driving force and resistive force. So this is a better term to use. I did mention this last week too. So look at part B. You have a block of metal that's fixed to one end of a vertical spring. The other end of the spring is attached to an oscillator as shown here. So the amplitude of oscillation of the oscillator is constant, and the variation with amplitude x0 of oscillations of the block with frequency f of the oscillation is as shown. So this little block here is connected to a spring, which is in turn connected to an oscillator. So this one, you know, is talking about forced oscillation system here because you're connected to an oscillator. So this is your resonance curve again. All right. Now, name the effect that is shown in figure 4.2. What effect is this graph trying to show you here? It's trying to show you that you reach A max when driving frequency equals natural frequency. This is a phenomenon called resonance. What's the effect shown in figure 4.2? It is actually resonance. And state and explain whether the block is undergoing any kind of damp oscillations. Is there any damp oscillations here? So you can actually say something that I mentioned earlier also. The peak is not infinite, thus oscillation is damp. I think this one, I say the peak is not infinite high. There's something like a typo here. You don't really need to write this. The peak is not infinite, so oscillation is damp. Now, part C is related to what I just mentioned to you. Examples where resonance is useful. State an example where the effect shown in figure 4.2 is useful. What is the example where resonance is useful? You can actually make use of a number of things here. The most simple one is in microwave ovens to heat food. Then there are two other answers that you can probably use. There's another answer you can actually use actually. In quartz crystal to produce ultrasound. This one you will revisit in another different chapter called medical imaging when it comes to production of ultrasound. So examples where resonance is useful, you can take these two examples. You can remember these two examples. The rest are actually not really inside your syllabus. You don't have any chapter covered that is related to this, so I don't think it's worth for you to remember. So here they say in quartz crystal to keep, in watch to keep timing, in tuning circuits of radio and television, in MRI to produce image scans of the body. There is no longer any syllabus in 2022 that relates to this, so don't need to remember this now. Just remember the first two because it's still related to your syllabus that you will cover. Okay, if we look at page 1, this one is June 15 P41. Okay, now if you look at question 4 on the page 1, state for an oscillating body what is meant by force frequency. Force frequency is just simply the frequency at which an object is made to vibrate. State, what is meant by natural frequency of vibration? So I mentioned that it is actually the frequency at which an object will oscillate when given an initial disturbance, or you can always just say frequency at which an object vibrates when there is no external force acting on it. This one is by far the best definition to use because this one always seems to occur inside your marking scheme. Now, for 3, what is resonance? It's a phenomenon in which a system responds at maximum amplitude to an external driving force when the driving force frequency is equal to the natural frequency of the body. If this one feels like too much to remember, just say maximum amplitude of vibration of the body when forcing frequency equals natural frequency of vibration. This is actually the simplest it can get, right? Now, for part B is asking you, state and explain one situation where resonance is useful. So for this particular case, just now I mentioned to you that there are 2 cases that you can remember. You can either say the vibration of water molecules in food at resonance that produces heat in a microwave oven. This is one example. Or you can also say vibration of quartz crystal at resonance to maximize amplitude of ultrasound waves produced. This one, as I mentioned, is under medical imaging. The exact principle of this will be covered in medical imaging. So right now, if I just mention this to you, you probably don't know what I'm talking about, but we will revisit it in medical imaging. Now for part C, in some situations, resonance should be avoided. Suggest one situation for a case where resonance should be avoided and suggest how the effects are actually reduced. Okay, now if you just read the answer first, vibration and resonance of metal plates on a machine that can cause the metal plates to loosen. And then to avoid this, change the shape or area of the metal plate. Now, reading this answer itself is a bit hard to imagine what are they talking about. This one is actually talking about your washing machine. Let's just say, for example, you have a washing machine right now. This is your washing machine. So you know that when you go and put in your clothes into your washing machine, let's just say, for example, these are your clothes. These are your clothes all inside your washing machine. When you put your clothes for washing inside the washing machine, the clothes will become wet with water. You'll become heavier, isn't it? So when your clothes are already heavy due to it being soaked with water, your washing machine will try to spin. So when it spins with the wet clothes inside, it will actually try to throw your wet clothes up and down the washing machine. So when it throws your wet clothes up and down the washing machine, it's actually applying some sort of periodic force on and off at a certain frequency. So in our case, let's call this frequency driving frequency. Your washing machine, on the other hand, also has its own natural frequency of vibration. So if you're unlucky enough where your driving frequency caused by the wet clothes being thrown up and down is equal to your natural frequency of your washing machine, you will have resonance if they are equal, driving frequency and natural frequency. So when you have resonance, now your washing machine now will actually vibrate a lot. It will vibrate violently. I'm not sure whether you have encountered this at your home before, where you switch on your washing machine, then suddenly at certain instances, it suddenly vibrates a lot, right? To the point that you actually have to faster switch off your washing machine. That is actually your washing machine vibrating at resonance. If you don't do anything to the washing machine when it's vibrating at resonance, the metal plates around your washing machine will actually start to come off, because you see this is your washing machine. your washing machines are fixed together by different plates, right? The front plate, the side plate, the top plate, and the back plate or whatever, they're fastened together by bolts or screws or whatever. You need something to fasten the plates to the washing machine. So if your washing machine is vibrating a lot, these screws or bolts will start to come off. So when they come off, your plate would also come off along with it. That's what this statement here is referring to. Metal plates on machine will start to loosen. An example of that is your washing machine. So if you don't want the metal plates on your machine or your washing machine to loosen, you make sure resonance does not happen in the first place. So what you do is that you make sure you change the natural frequency here so that it will never come to a case where driving frequency equals natural frequency. So how you do that is you change the shape or area of your metal plate. This will cause your natural frequency to change. Another thing you could also do is to place strengthening struts across the plate. What this means is that you just put some sort of bar across it to prevent the plates from coming loose. Okay, that is what we mean by strengthening strut. There's a video animation that can show you what I mean. Just let me try to open it up. So you should be able to see a new screen share here now. This one here, what you're seeing is a washing machine. When I play the video later on, you will notice that the person put some sort of brick inside and then switch on the washing machine. So the guy is putting a brick inside. No, it's not a brick. It's some sort of metal piece. And then you switch on the washing machine. So as I mentioned to you, as the washing machine spins, it will throw your mass up and down, causing the object to vibrate. So your driving frequency equals the natural frequency of vibration of your washing machine. It vibrates violently like this. So you leave it there, the plate will start to loosen up. So let me just keep it playing for another 5 or 10 seconds to see how bad can it go. In the worst case, it becomes something like this now. All right. In the worst case, it becomes something that looks like this, right? Where it's completely breaks down. All right.